First of all, agenda for this week. Chapter 7 will continue covering on chapter 7. Hopefully this week I can finish a bug and boost. We'll see. And then quiz number 5 is going to be due this Friday, covering pages 245 to 305, 245 to 305. I believe this is on buck converter. Can double check on that one. And then this week's lab, yeah, this is something that I was debating over the weekend, which experiment I should do for this week. Seems like if we're doing push pull or any of the other converter, it seems to be too early, especially the isolated one, because the plan is for you to experiment with push pull or flyback, one of the two. But then I thought that's probably too early. You need to know the concepts first well before you could do a push pull. Now this is not the same as the other ones, uncontrolled rectifiers, control rectifiers, and AC to AC. Those I could go over those topics at the beginning of the lab. But push pull and other ones, I think it would require longer time to cover if I have to do it before the lab. So it's not going to be a short lecture. That's what I'm saying. If I have to do it in the lab, so I would rather wait until next week before you can do the experiment on isolated topology such as push pull or flyback. We'll see. But looks like over here I updated the agenda for the labs. So for this week, you'll be doing the final project. So hopefully by after covering some of the concepts today, should prepare you for doing the final project. So please use the lab time today to start working on the final project, ask questions or get started with the project, with the equations, with the component selections, etc. Right. So please do that for this week. Still attend the Zoom session though, okay, for this week. So it's just like a regular labs. You need to be in the Zoom session, and then yeah, we'll discuss the final project during that lab time. Any question on that one? And then next week I'll put together simulation experiment for isolated topology. I need to decide which one. Okay, I'll let you know. And then week number 10, we'll do the inverter. Okay. Any question on this? Any question at all? Go ahead.
Only is this week, correct? No homework?
Yes, there's no homework yet. So homework's gonna be next week, Friday. Right. So I need to cover enough material first before I can assign you homework.
Okay, so not this Friday.
Not this Friday, yeah, just quiz.
Okay.
Let me see, did I write that on here? I hope I did not. So lectures, quiz, lab, yeah. So no homework this Friday, just quiz. Any other questions? Right, not. Let's start with our first converter, buck converter. All right. So buck converter is a step down converter. We'll see later why this is a step down. Mainly is because of the transfer function, V out over V in. And again, you'll see that after we derive the transfer function. So my plan is to go over how to analyze the circuit first, the different states of the circuit. Of course, before we do that, we look at the structure of the circuit, the topology, right? And then we analyze the circuit, derive the transfer function, and then look at how we can understand or draw or sketch waveforms within the converter, right? So that we are familiar with the type of waveforms we're dealing with within a DC to DC converter. I think that's important for us to do it. I realize that you can always simulate this, but simulation is just a tool, right? It will be, I think it will be much more useful if you use the tool, if you understand what goes behind the tool, right? So not just using the tool, but understand what goes behind it, especially graduating from Cal Poly with an engineering diploma. You're going to be an engineer, not a technician. So you need to understand what goes behind concepts, as well as equations, as well as circuit, not just simply using the tool. So that's why I'm forcing you to understand or to know how to sketch waveforms within a DC to DC converter. And then after that, once we understand how waveforms is shaped in the DC to DC converters, then the next thing would be sizing components, which is also important in the design process, right? So some of the sizing phase of the design is based on waveforms. So that's the reason why it is also important for you to understand different waveforms in the converter, because we use those to size components, as you will see. Okay, and I think that will be it. That's kind of the steps in covering DC to DC converters. Doesn't matter if it's a buck boost, push pull, flyback, forward. Those are the steps that I'll be going through for each one. Okay. All right. Okay, first thing, or not only one, but several things I need to mention about DC to DC converters. This is not only for buck, but also for other ones. You already know this from the lab, is that DC to DC converter mainly will have feedback, right? It has to have a feedback to be able to control the output voltage or maintain the output voltage, regulate the output voltage, right? DC to DC converter by itself, right, will not work properly without any feedback controller. Okay. Now in this class, we'll only be learning about the DC to DC converter side of this, or we call it power stage. I'm sorry. This box right here is the power stage. We're not going to go into the controller. We're just touching that a little bit by learning how to set the controller as you did in the lab. Remember, you do the voltage divider, right, to set the output voltage. That's the extent to which I'm willing to cover for this class, because beyond that is going to be another class. Okay, this controller stage right here is this is another class, a huge topic by itself. All right. So for EE410, we'll focus on the power stage. So we have the power stage, controller stage. This is a must. In many textbooks, it doesn't show that converters must have controller. But this is Cal Poly. We know that this is a learn by doing school. So I want you to know that practical DC to DC converters must have a controller. Another thing, that's the first thing. Again, in many textbooks, they only show you the power stage for a buck. This is an example for a buck converter. I'll go over this more later. Right. So power stage is where power flows, or where the main currents flows in the circuit. Right. So you deliver power from the source to the load, and in the process, this power translates into currents. Right. So major currents that flows in the circuit, right? Those major currents flows through what we call the power stage of the circuit, right? And so as a consequence, those components will be relatively big. Okay? So the switch, the diode, the inductor, right? These are the three main components for a buck boost and buck boost. You will always see these three main components, the one that I box in right there. Right, so when we look at boost, it will have the same three components. When you look at buck boost, it will have the same three components. Right, these are all power stage. Of course, in addition to these three main components, you have also other power components, such as output capacitor, which is needed to get better DC at the output, because we want DC to DC. Remember that, right? We want DC to DC, meaning the input characteristics will be flat, both voltage and current, assuming that we have ideal voltage source here. So of course the voltage is going to be flat, but that doesn't necessarily mean that the input current will be flat. You'll see. Same thing with the output. The output, we want voltage and current to be flat. not necessarily what you'll be getting, right? So therefore, we need a way to make those voltage and current waveforms smooth, or looking more like a DC. How? By placing a capacitor. Okay. Now, again, in many textbooks, that's what you'll see, right? And again, this is our a learn by doing school, right? I'm going to go a step ahead of that one, right? A step more than this one, right? Out of this class, you have to understand that in real world DC to DC converters, you must have the first one, the controller, the second one, the input capacitor right here, right? So this is one thing that's always missing from, like I said, many textbooks. Right? They always show the output capacitor, but rarely show the input capacitor. And that's fine, because the way textbooks draw this circuit is by having an ideal source. So when the source is ideal, you don't need input capacitor. But what we have in the real world is not an ideal source, right? We have real world source, and this source may come from a DC bus, right? That has some parasitic components, right? For example, resistance through wires, or internal resistance of the source, as such. So then, because in real world we're dealing with non-ideal voltage source, therefore you need this input capacitance. You must have this. If you look at any DC to DC converters in real world, they will have this input capacitor. It will not work without this, right? Reason why? Because this is a high switching frequency circuit, right? So for high switching energy, the real world source will not be able to keep up. It would require help from energy storage component. So what better component you can use, right, for doing that, right, for supporting voltage source than the capacitor right here. Okay, so that's the reason why we need this. And there is another purpose for this one as well. This is to absorb some transient as well, coming from the input, right, and also to filter the input characteristics of the input current characteristics of the converter. Right, so many purposes. So one more time, okay? Feedback controller is a must. Input capacitor is a must. So in this class, we're going to learn how to size both output capacitor and input capacitor, both. Okay. Here's an example of a circuit, a buck converter.
About the
Go ahead.
If you scroll up to B, it looks like the output capacitor is polarized. I was wondering and see why. Is it just like why?
Yeah, thank you for bringing that up. It's just the way I draw that. This would be polarized, all of them.
They should all be. Okay.
Yeah, because it's a DC, right? So polarity matters. So
Yeah.
plus minus, plus minus. So both of them should be polarized.
Thank you.
You're welcome. All right, and then here is an example of circuit that I copied from Maxim. Right, so to show you an example of a real world circuit, or not real world, but from a real world data sheet, I should say. Even from this data sheet, you can see that there's an input capacitor there, right there. Okay, and this one is also showing what do you call this, PFET MOSFET. I almost forgot about that. Yeah, so here's a PFET right there too. Right, the reason why we use PFET, because it's what we call high side MOSFET. Right, a high side MOSFET is a MOSFET that whose gate is not grounded. Right, so gate to source. This is what is it? Gate to source right here, right? And you can see the source is at switching node, and the switching node is not constant. So therefore, if you put an NFET, it's not going to work, because this is going to be changing unless you do something else, right, to this gate. Right? So a simpler way is to use PFET. Their way is going to go from gate to drain right here, right? So drain is what you call it, constant right there. Okay, so now you have a stable gate to drain signal. Okay, to drive the PFET. The problem with PFET, even though this is the simpler way of building a buck converter, is to use PFET. The problem with PFET is that PFET is typically more lossy than NFET. What I mean by that is that the RDS on of PFET is typically larger than NFET. Why? I don't know why. you can ask Dr. Braun of why PFET is more lossy than NFET, but that's what I know, and that's what I've observed is that PFET usually has more RDS on than NFET. So in many situations, many controllers allows you to use NFET rather than PFET. So instead of PFET right here, you can actually have the other type, which is the NFET, but they do something else on the source side right here. So instead of connecting it straight to the what do you call it, the switching node, it does something else too. You'll see. Right. Any question on this? All right. So reason why I want to show this picture right here with PFET. That's one of the common interviews, one common interview questions from companies. They ask you, okay, draw a buck converter with PFET. So right there is the picture of a buck with a PFET. Okay, just in case you got asked for that question. All right. Then we have a different version of a buck and also boost and buck boost. Doesn't matter. It's called synchronous. In which case, I am replacing the diode with another MOSFET. So this is called synchronous. So if somebody asks, what is a synchronous buck? Simply means that you replace the diode in a buck converter with a MOSFET. So if I go back up again, see that diode right there? It's a Schottky diode because it's fast. You don't want to use PN. You have to use a very fast diode such as Schottky. Because it's high switching frequency, right? So you need a fast diode. So this diode, if you replace with another MOSFET, that's called synchronous. Now you can see that the top MOSFET, which is what I call high side MOSFET, has a PFET, right? The low side MOSFET, right? Because the source is grounded right there. That's the gate, that's the source. The source is grounded, so the source is stable. So now you have a stable gate to source signal to turn on and off the MOSFET. Therefore, you could use an NFET. That's actually a PFET, huh? This could be an NFET. So sorry about that. You can change that to an NFET. It doesn't need to be a PFET. It could be a PFET, but why, right? So I think if it's a PFET, it's going to be giving you more headache. So sorry about that. This would be an NFET. The arrow is going into instead of out. Sorry about that. That's a typo right there. I need to fix that. So this is a PFET. This should be an NFET. Okay. Here's an example of a synchronous buck converter. You see both of them are using NFET. Right. The bottom ones, you just connect the gate straight to the ground. But look at the top side or high side MOSFET. Right. It is connected to the switching node, but it does something else. This is called a bootstrap capacitor to make sure that the gate is always larger than the source to be able to turn on the MOSFET. Right. That's the condition for you to turn on the MOSFET. All right. You can see that the diode is being replaced by a MOSFET. High side, low side. Okay. So if somebody asks what is high side MOSFET or high side switch, what is low side switch? Now you know the answer. A high side switch is the one whose source is not grounded, is at a fluctuating node or fluctuating potential, whereas a low side, the source is at a stable node, such as ground, like that, or ground, period, right there. Any questions on this? So just several, practical comments before I start the theory behind. Go ahead.
Up above, what does the source line mean? Does that just mean they're grounded?
Where is it? The source, what is it? Sorry?
The diagram above.
Oh, above.
The synchronous buck converter.
Yeah, this one?
Yeah, so when you look at Q2, that source having that line to it,
Yeah.
does that reference the source being grounded? Is
Yeah,
that what you're saying?
You mean this one?
Sorry, the line to the right.
The line to the right. This one?
Yeah.
That's for the controller circuit.
Yes, so this is
Okay.
connected to PWM controller. So you have a driver circuit basically. So if I were to draw a driver circuit as PWM out, you can connect it to there.
So instead of it having a diode there, it's just actively controlling it like an active rectifier.
That's correct, yes. Yeah, so just keep in mind that in order to be able to control MOSFET, you need to have a gate signal, right? Gate to source signal. Right, for this one, yeah, so you just connect this gate into a controller right there. Does that answer your question?
Controlling the gate, you control the source. Okay.
Yeah, the source you don't need to control because it's at a stable ground, right? It's basically 0 here.
Oh, that's for the gate. Okay.
Yeah, this is gate. So you can send your PWM there, right? Which is going to be relative to the ground, right? So then when the gate is high, well, that's high with respect to the ground. That's going to turn on the MOSFET, assuming, of course, it's above the threshold.
Good job.
Does that make sense to you, or?
Yeah, that makes sense. It's just a different way of notating or representing the PFETs than I'm used to. So thank you for the clarification.
Okay. Okay. Yeah, sorry. Change this to NFET. I asked you earlier. Change it to. I was answering the question based on NFET, not PFET. So go ahead and change that to, NFET. The arrow going in. That's a typo right there. Sorry about that. Any other questions? So
Does
yes.
that mean for these chips that we're seeing on this page, does that mean that we're frequently supplying the control signals ourselves to these chips?
This chip right here?
Yeah.
Yeah, so this chip is a controller chip, right? You can see feedback right there. What is it, the feedback? Vout, yes.
Okay, yeah, I see.
See that feedback right there? So it senses the output voltage and then process that output voltage and produces PWM signal to be able to regulate the output voltage.
Got it.
By sending a signal to both the top MOSFET and the bottom MOSFET. So it has two outputs.
Okay.
There and there. Okay, and this has to be synchronous, right? That's why that's the reason why this is called synchronous buck, because the switching signal has to be synchronized between these two MOSFETs. Meaning, if the top one is on, the bottom one must be what?
On?
Off.
If the must be off. You
Off,
cannot have the two on at the same time. Go ahead and try that. You're gonna get a short across the input, right? If you do that. So
that'd just be implemented using just a simple NOT gate.
And then also there's a logic that provides dead time between the two.
So there's small like timings that are important.
Very important, yes. Yeah, it's called dead time. So if this is for the top MOSFET, the bottom MOSFET will be the complement of that. But in practice, you're gonna have to provide, or the controller has to provide a very small amount of time, around 0.5 to 1%. To 1% of the period of the period, right? For that time. Right. This is to make sure that the two MOSFETs are not on at the same time, because having the two conducting at the same time will be dangerous to the source, right?
So you can't have just one signal with an inverter. Like,
Unless you have to have two, right? Because these are both MOSFETs.
I was saying, like, you can't have one control circuit going into like Q2 and then an inverter to that tied to two with that same input signal because you need like a little bit of a delay, kind of.
Yeah,
You need
if
one
that-
of them to be smaller duty cycle.
That's correct. Well, it doesn't. The bigger and smaller duty cycle, that will be a function of output and input, as you will see, right? Because the top one could be a smaller duty cycle than the bottom one, right? But to answer your question, if you want to build it from scratch, then yeah, you do that, right? You invert the signal and you provide some more logic circuit to add this dead time. But nowadays you don't need to do that, right? You don't need to build the controller from scratch because this company, for example, Maxim, provides you with that already, right? So all you need to do is buy this controller, for example, if you want to do a synchronous buck, and it'll provide the required signals for both the high side and the low side. Does that make sense? Or does that answer the question?
Yeah, thank you.
Yeah, so this controller provide.
Is supported.
I'm sorry?
How do we determine the current load that it can support, like the max current output?
Okay, that's you're getting ahead. Okay, you're getting ahead. But specifically on this synchronous, any more questions?
There's still a Schottky present in the circuit, and I'm curious as to what its function is.
Very good, very good. So this is actually for 11 stuff, right? But I'm gonna explain it briefly. The reason why we have that Schottky. Very good, right there, right?
Yep.
Right? That Schottky is actually across here. It's the same thing, right there. So I can erase this and I can redraw it that way. So that Schottky is in parallel with that MOSFET, the bottom MOSFET, right? The reason being what? Anybody? Let's see if we can analyze the circuit. Why do we need the Schottky?
Is it a
During the
protection?
dead time, like the inductor has to be able to still have current easily go through it, or it's going to cause a voltage spike.
Very good. Awesome. That's the answer. Remember this dead time right there? The two MOSFETs are not on. The two MOSFETs are off. If that's the case, what do you do with L, right? It's going to get pissed, right? If its current is being stopped. If its current is being interrupted, it doesn't have any path, it's going to get mad. How does it show that it's going to get mad? You're going to get a spike right there and blow this MOSFET, right, to non-existence. Okay, so that's why you need a path for that inductor current to kick back, right, and flow its energy, freewheels its energy. So it is kind of interesting because in the first place we got rid of this Schottky, right, with the MOSFET. But then at the end, you're going to have to add that Schottky back. But
so it's over voltage protection for the FET?
Over voltage as well as freewheeling for the energy.
Okay.
Right. And keep in mind that this Schottky is going to be different from the Schottky that you see here, even though they look the same. The function is different. This Schottky right here, its function is for discharging the inductor, strictly discharging the inductor, right? Over here, the Schottky is for dead time. See that dead time that I just told you earlier, okay? And so this Schottky is going to be smaller when it comes to current rating. So that's only conducting for a tiny bit of a period, whereas the previous Schottky right here is conducting for a significant amount of time within a period. Does that make sense to everybody? The difference between the top Schottky and this one that we use for synchronous? Yep. Okay, good. All right, that's as much as I could, as much as I would like to cover for synchronous. At least you know the basic. Right? At least now you understand what a synchronous MOSFET, synchronous buck is, or it doesn't have to be buck. Synchronous boost, synchronous buck boost. It just means that you replace the diode with a MOSFET. Okay. All right. I think I've covered this, and this is another thing that I mentioned in the lab as well. The difference between power stage and controller stage. I would like to emphasize that as well, because this is important when you lay out the circuit, because designing the circuit is only the first part of the design phase, right? The next step would be to actually build the circuit. So when you actually build it on a PCB, you want to be able to lay it out properly, right? And so you can see the contrast here, right, in terms of placement of components for power stage versus controller stage, right? Power stage is where, what I said earlier, where major currents flow, right? Therefore, the component is going to be bigger right there, right? So you can see the bigger components, right? These are power stage components, right? And then you can see the smaller components right there. That must be controller stage. Where's my pen? Right here. So here's controller stage. And here is power stage. But even on the PCB, after we build it, we can tell the difference between power stage and control stage. You cannot mix them up. You cannot put the controller stage in between, for example, power stage. Why not? Because power stage is where the noise exists. This is a switching circuit. So, within the power stage, you have switching noise. Whereas controller stage it processes voltages, right? So you want this signal here within the controller to be clean. And this is noisy. Is that how you spell noisy? All right. So you don't want to mix clean signals with noisy signals. Definitely, right? So that's why when you lay them out, you're going to have to separate the two. Okay. Even with the grounding, you would separate the grounds first before at the end you connect them with very tiny, oh my god, very tiny resistors. Sorry about that. It does that all the time. I think I have a picture to show you that, maybe right there. This is perfect right here. Is it perfect? It is. Okay. Kind of. Notice that the way Maxim drew this, right? Look at the different pictures of the different symbols for the grounds. It tells you that those two are separate grounds, but at the end they combine the two. Usually it's using a small resistance, tiny resistance, right? As an attempt to isolate controller grounds with signal grounds, we call it signal grounds with power ground. You can see all of the triangle, those are power ground. Right?
Ground bounce is gnarly.
Oh yeah, it is. They're very noisy. So you don't want to mix them up with signal ground. Any question on that part of the discussion? Right. Okay, I think I'm ready to start with buck converter. All right, buck converter. Let me go to empty page here. So we're gonna cover 3 basic converters, non-isolated basic converters in this class: buck, boost, buck boost. And as I said earlier, if you understand buck fully, then you will understand boost and buck boost easy, right? So that's why it is important that, and I'm glad that you attended the class today. We're gonna talk a lot about basic concepts here. So first thing first, a buck converter. If somebody asks you, how do you draw a buck converter? Just remember my name. Okay? My name is, well, you know, or maybe you don't, but my name is this, right? Just remember my name, because my name starts with T, letter T. So start with T, right? That's how you start. Or that's how I would start. If somebody asks me, I can draw a buck, a boost, buck boost, I start with the first letter of my name, T. So just remember my name, okay? And then for a buck converter, I'm going to use red. Remember the 3 main components: a switch, a diode, and an inductor. A buck converter has a switch at the front end, inductor at the output end, right? And then the remaining component would be, what is the third one? That's got to be in the middle, the diode. That's a buck converter right there, right? So you start with the letter T, and then place the switch at the input, right? And then place the inductor at the output, right? And then the third component will be the last branch of the T network. Got it? And then after that, you just add the other components, right? Capacitor here, and assuming you have ideal source, then you don't need the input capacitor. But as I mentioned earlier, if this is non-ideal, then you have to have this as well. Input capacitor as well. Any question on this? So
Hey, I'm confused. What after the letter T? How is your name helpful in memorizing the circuit?
it's not. It's just.
I thought there was a thumbstick there.
It's not. It's just how to start. You know. After that, then
Okay.
you know you're gonna have to add capacitor at the input and the output, right? So start with T, and then start with the components, and then after that you add capacitor out on the output, capacitor at the input, and you're done. Yeah. Okay. So only is helpful to start. Any other questions?
I thought it was pretty helpful.
I thought so too, because it's my name. You know, that's why I will always remember my name.
No, it makes sense. Power electronics professor, when you're wondering how to draw a buck,
Yeah.
start with a T. No, it makes sense.
Yeah. That's what I thought. But you know, that's my preference. It's up to you. Same thing with boost. I'm gonna draw the other ones. Okay. So you can see if somebody asks, okay, how about boost? Start with my name, T, the letter, first letter, T network, right? For a boost, is the opposite of a buck. Remember, in a buck converter, you have switch at the, you have inductor at the output, right? For a boost, the inductor moves to the input, right there, right? And then you just rotate counterclockwise from a buck. You have a boost now. And then that's it. And then you add capacitor on the output, capacitor at the input. That's it. Okay. That's your boost. Of course, this is only the power stage. Okay. And then how about buck boost? Maybe I should use, I should not erase that buck, but I did. For a buck boost, tell me how do you start?
With your name?
With my name, yeah. What's my name, by the way?
I'm drawing a blank.
NFN. My name is NFN. Oh, so start with T, right? And then buck boost. Right? Buck boost is a combination of a buck and boost. Right? That's why it's called buck boost. If you remember buck, then you remember boost, then you remember buck boost. Right? A buck means at the input you have a switch. Right? Let me see. Let's use red. So buck, the input looks like a buck, the output looks like a boost. Right? That's why it's called buck boost. All right, and then you know that boost is the opposite of a buck, right? And remember what's on the output of a boost? I'm not expecting you to remember, but remember, sorry, for a boost, the output is a diode, except now the diode is backward for a buck boost. So if you have the switch here, the diode here, that means in the middle, it must be, which one?
Inductor.
Yes, right there. That's a buck boost. Right. So that's why I said, you know, if you understand buck, then even drawing boost and buck boost will be easy. Right? Any question on this? So start with T, the T network. Of course, I'm only joking when I said my name, but if that is useful, go ahead and use it. But I always start with the T network, with a T, you know, network, right? You call it T network. And then start placing the components that way. For a buck, input is a switch, output is inductor, middle is the diode, right? Boost is the opposite, so inductor moves to the front, right? And it's just rotate counterclockwise with respect to a buck, right? Then you get inductor, switch, diode for a boost. Buck boost is a combination of a buck and boost. The input looks like a buck, Input looks like a buck right there, right? Has a switch. What is it? Oh, come on. Does it again. Input looks like a buck, right? Has a switch. Output looks like a boost that has a diode, right? Okay, let's go back to here. Very first thing I would like to go over is buck transfer function, because from here we would know how output voltage is related to input voltage. In order to do this, there are some conditions that we have to be aware of. The buck transfer function that I'm going to derive here is going to be only valid under steady state condition. Steady state right there. And then ideal, meaning all the components are ideal, no losses. And last one, CCM. CCM stands for continuous conduction mode. I actually skipped that part. Hang on a second. Let me go back several pages. I believe I have a picture of that. CCM, does it again. Right there. Right, this is page, what is that, 269. So CCM stands for continuous conduction mode. It refers specifically to inductor current. Remember in buck boost and buck boost, we have inductor. So the current through that inductor determines the operation of the converter, right? Very important. So when the inductor current is always above 0, such as this one right there, see this one is always above 0, right? And I'll explain why the shape is this way, okay? For now, don't worry about why the shape is a triangular waveform. But you can see that inductor current is always above 0. If that is the case, when you operate the converter, the inductor current is always above 0. That means the converter is operating in CCM, continuous conduction mode. Okay, as opposed to what? As opposed to the red one right here, that's discontinuous conduction mode. Why is it called discontinuous? Because you can see clearly from here, the current through the inductor goes to 0, stays at 0. Go up again, goes down, and then stays at 0 again. It goes up again, goes down, stays at 0 again. So that's discontinuity in the inductor current, okay? So the red one is called discontinuous conduction mode, DCM. The borderline between the two is called BCM right there, boundary conduction mode, right? So remember that boundary conduction mode is the boundary between CCM and DCM, meaning the minimum point of the inductor current right there touches 0. See that? It just touches 0. Okay, any question on this? So now you know the difference between CCM, DCM, and BCM. Okay, let's go back. So the operation steady state analysis that we're doing in this class is going to be based on CCM only, not DCM. And again, the reason why, because majority of DC to DC converters are designed based on CCM, not DCM. Okay, right there, steady state, ideal, and CCM. Now, in order to derive transfer function for a buck converter, boost converter, buck boost converter, you could have different ways of doing this. I'm going to show you 2 ways, the long way and the short way. I'm going to show you the long way first so you can appreciate the short way. Right? And I think it's important for you to also know different ways of deriving transfer function. Okay, all right, here we go. For the long way, right? If the circuit is already operating in steady state condition, that means if I look at the inductor current, right? Again, don't worry about why the shape is a triangular waveform. Right? Let's say that's the inductor current waveform, right? If it's steady state, then let's say this point right there, right? T1. One period later, oh, no, not that one, sorry. Sorry, wrong concept. Maybe I just show you the inductor current that I have earlier. That way I don't have to draw the inductor current. because that would be better to see. If it's steady state, if the converter is already reaching steady state condition, let me erase this. Tell me if you disagree with me, okay? If it's steady state condition, then the change in the inductor current when it's going up, right here, when it's going up, because the inductor current is going up there, right? The slope is positive. So the change in the current, which is what I call delta IL, let's say plus, right, should be equal to the change in inductor current when it's going down or sloping down that way, right? So right here, delta IL. I call it delta IL, let's say minus. So do you agree with me that in steady state, delta IL plus delta IL minus should be equal to 0? Do you agree with that statement? The change in inductor current for when it's going up should be a positive change, right? Bigger value minus smaller value should be a positive change. But when it's sloping down, it should be a negative change, right? Smaller value minus bigger value should be a negative value. But the magnitude of the change, delta, should be the same for both because it's steady state. Anybody disagrees with that? Okay, so if everybody agrees, then that's the basis of how I would derive the buck transfer function, okay? So let me go back right here, right there, right? So delta IL on, which I call delta IL plus, plus delta IL off, which I call earlier delta IL minus, should be equal to 0. Okay, so now I'm going to have to find the equation for delta IL on, delta IL off later. Okay, and then another thing is that in deriving the steady state transfer function, we will need to express T on and T off of the duty cycle. Right. So in many cases, including the converters that we'll discuss in this class, with the exception of only one converter, which is the push-pull. In other cases, you know, buck boost, forward, and push-pull. T on, not T on. Yeah, T on is always dt. How do I get that equation? From this, right? Remember the definition of duty cycle? This is the definition of duty cycle, isn't it? The duty cycle is T on over T. So from there, I could solve for T on. So T on is equal to dt, right? So we've seen that before. Right, so T on, what is T on again? T on is the amount of time the switch is conducting, right? That's the duration when the switch is conducting. That's T on. That's equal to dt. What is T? T is the switching period. D is duty cycle. So if I know T on, then I should know T off, right? Because T off will be the remainder of the time, right, within a period. So T off mathematically should be the entire period minus T on, right? So it should be T off. Again, what is T off? That's the amount of time the switch is off, the duration of the time when the switch is not conducting. Right? That's going to be T minus T on. And if you simplify the equation, you get 1 minus D times T. So what I want you to do is to memorize these two, right? Memorize that T on is equal to dt, T off is equal to 1 minus D times T. Can you do that for me? Right, because that's going to be convenient for you to memorize this when we're deriving a transfer function as well as other things when we analyze converters. Okay, so T on is dt, T off is 1 minus D times T. Okay, moving on. All right, again, my objective now is to be able to derive the transfer function using delta IL on plus delta IL off equals 0. If I can find the equation for delta IL on, equation for delta IL off, then I should be able to get the transfer function, as you shall see. All right. All right, so I'm going to start with the buck converter again. Assuming ideal source, therefore I don't show the input capacitor. There are only two states of the buck converter, right? Either the switch is on or the switch is off, nothing else, right? So what happens when the switch is on? Remember this, there is actually a diode here, sitting right there, right? And there's a switch right here. When the switch is on, you can see that the cathode is connected to the plus side of the source. The anode is connected to the ground. What do you think is going to happen with that diode? Of course, it's going to be reverse bias, right? Because the anode is less positive than the cathode. So that would force the diode to be off, reverse bias, just like this. So this is state 1. And this happens when you turn on the switch. So when the switch is on, diode is off, then what's going to happen? You can see we are connecting the source to the load. You can see there is a connection now, right? Electric connection, physical connection between the source and the load, right? So now energy flows through this switch into the inductor and into the load that way. Okay. Now, remember what I'm trying to do here is delta IL. What is delta IL again? The change in inductor current. So I need to focus on the inductor because I'm looking for delta IL, right? Current through the inductor. All right, so if that's the case, if I reference the voltage across the inductor to be, so this is important, the reference voltage is plus minus that way, okay? That's the reference voltage. The instantaneous voltage across the inductor may be different, of course, but I need to put a reference, right? So the reference polarity of the voltage across the inductor is plus on the left, minus on the right of the inductor. Okay, so then again, when the switch is on, you can see that this portion of the inductor is connected to the source, and this is connected to the load, right? So therefore, voltage across the inductor, as you can see from here, what is voltage across the inductor? Simply V in, right, this node, minus this node right there, right? So what is this node equal to? That's V in with respect to ground. What is that node right there equal to? That's V out with respect to ground. So therefore, voltage across the inductor when the switch is on is V in minus V out. Any question on that one? Okay. So voltage across the inductor when the switch is on, that's why I call it VL on, is equal to V in minus V out. And we know the other equation for voltage across the inductor is L DIL dt. Why is that important? Because I'm looking for delta IL. You can get delta IL from here. See that at high switching frequency, right? I'm assuming very small ripple, then you get the approximation right here. So delta, so if I solve for delta IL over delta T, then you get V in minus V out over L. And then for high switching frequency operation, that's approximately equal to delta IL on over delta T on, right there. Right there, okay? I'm looking for delta IL on. So now I have the equation, right? That delta IL on over delta T is equal to V in minus V out over L. I can solve for delta IL that way, right there. Okay, so now I have the equation for delta IL. Any question on this one? Any questions? Make sure that that's clear. I'm going through this slowly. When it comes to the boost converter, it's not going to be slow anymore. I'm going to go faster. Good? All right. Next, the second stage. I'm going to turn off that switch. Right? If I'm turning off that switch, what happens? First of all, physically, you are disconnecting the source from the load. There's no physical connection anymore, right? The switch is like the gate that opens and closes, right? If the gate is open, then you are stopping energy to flow from the source into the load, just like you see there. There is no way energy will flow from the source to the load at this point, right? Because I opened the switch. Any question on that? Okay, if you agree with that, then I have a load right there, right? And this voltage, right, that's going to be a regulated voltage. Remember the feedback, which I'm not drawing here. So the voltage is regulated. So you got V, and then you got resistor. So V divided by R gives you current, right? So even though the source is disconnected, the load is still requiring current or energy. So where is that? Where does that energy come from then? Anybody?
The inductor.
Yes. That's why we need that inductor as the energy storage, right? So that when the source is disconnected from the load, this load can still receive energy from the inductor. In other words, when the switch is off, right, this inductor must discharge its energy, must release its energy. Agree? Then when it's releasing this energy, I know that the reference voltage is plus minus that way. I just explained to you earlier. But the instantaneous voltage of this inductor, what's going to happen with respect to the reference voltage? Anybody? Is it going to be plus minus that way? The instantaneous voltage is going to be minus plus. The actual voltage
Minus plus.
is going to be minus plus because it's releasing its energy. That's why, as you learn from circuits, right, its polarity flips, right? So instantaneously, the instantaneous polarity of this voltage is going to be minus plus that way. So it's going to be negative with respect to the reference, okay? But keep in mind that the actual voltage of this inductor is now minus on the left, plus on the right. If that is the case, if this is actually minus and this is 0, that's still ground, right? Then what happens with this diode? Well, now I know that anode is at 0, cathode is at negative voltage. Which one is more positive, anode or cathode?
Anode.
Then now we understand why when the switch is open, forcing this inductor to discharge, and in turns will force this diode to conduct, right? Works out beautifully that way, right? So now we have a path for this inductor to discharge. Otherwise, if there's no path, inductor gets pissed again, right? But now we have a path for the inductor to discharge. All right, and in the process, of course, supplying energy to the load. Any question on this? All right, what about voltage across this inductor? When you determine the voltage across the inductor, you have to go back to the reference. Reference is plus here, minus here. So to be consistent, right? So you can see that the voltage across the inductor at this point is, well, this is pulled to the ground. So I know this is going to be 0. And here is V out right there. That is V out with respect to ground. So you can clearly see that the voltage across the inductor is going to be minus V out. Any question on that one? No? Okay. Which consistent with what we observed earlier, that at this point, the voltage across the inductor is actually the opposite of the reference. So that's why you have negative sign in front of V out. Okay, so now I'm going to do the same thing. VL off, voltage across the inductor when it's off is equal to minus V out. That's equal to L DIL off dt. Except now this dt must be T off. Right? Before was T on. I forgot to mention, sorry. Before it was T on. Right here. That dt is T on. See that? And we know that T on is equal to dt. Right? And then now is T off. And what is the equation for T off? Anybody? Well, it's right there. This is the one that I want you to memorize. Remember, the equation for T off is 1 minus d times T, right there. Right. So now we have delta IL off over delta T off. Right. And then it's equal to minus V out over L from this equation up here. And from there, I get delta IL off. See that? Delta IL off equation. Now I'm done. I'm done in terms of deriving delta IL on and delta IL off. All I need to do now is substitute those equations into the previous equation I have, right here, that delta IL on plus delta IL off must equal to 0. Go ahead and plug in the equation for delta IL on that we derived earlier and delta IL off that we derived earlier as well, right there, over here, for delta IL on and for delta IL off right there. And now the rest will be just algebra. See that? things cancels, that L cancels, T cancels, and at the end, look at the transfer function. At the end, you have the transfer function that relates output voltage to input voltage. So V out average is equal to V in duty cycle times V in. That's the transfer function. Or you can write it this way: V out over V in is equal to duty cycle. Right? What's great about this equation is this, right? At least to me, it's very exciting equation to have. You know, very useful equation, first of all, and then it's very exciting to see that output voltage is only a function of duty cycle, right? And I know there's V in there, but you know, if V in is fixed, then you know duty cycle is the only one that's gonna affect the output voltage, right? So given a fixed input voltage, you need to adjust duty cycle only to be able to change the output voltage. That's number one. Number two, which is also exciting, especially from EE point of view, right? This equation shows us that if you operate, this is very important, so please listen. If you operate the converter in CCM, remember it's CCM, right? Then the output voltage, right, is not a function of output current. There is no output current there, right? There is no I out in that equation. So output voltage, right, is not a function of the load, which is great, right? Because if you look at this circuit right there, right, theoretically speaking, of course, it doesn't matter what current you are drawing here, output voltage should not be affected, ideally, of course. Does that make sense? Why? To me, at least, this is a very exciting equation to have. It's independent of the load, right? And that's great news to me. That's less headache, right? To me, by not having I out there, right? Okay, so those are the two important things about this transfer function. Number one, it's only a function of duty cycle given a fixed input voltage. Number two is independent of the load, right? Now, guess why people like to use converter, DC to DC converter in CCM rather than DCM? Can you guess why, or what happens if you operate this in DCM? What happens to this transfer function? What's going to change? Can you take a wild guess?
There's going to be a function of the load current.
Very good. Yes, exactly. Exactly. So if you operate the converter in DCM, you're going to see I out there, right? Or R. It doesn't matter, right? R or I out, right? That's more headache, right? You have to deal with current in addition to duty cycle, right? So here is only duty cycle. So that's in terms of controller, that's awesome, right? That's a simple controller to make, right? If it's only a function of duty cycle. Make sense, hopefully? So that's why, again, when I first saw this equation, way back when I was a student, I was like, wow, this is actually pretty awesome, to have a transfer function of a power circuit, not just any circuit, power circuit that carries a lot of currents to not be a function of current at all. That's, that's just wonderful. Okay, any questions? Okay, so now I just showed you the long way of deriving transfer function. I'll show you the very short way, and you're gonna love this. And the reason why I stressed on volt-second balance some time ago, right? Volt-second balance states that the average voltage across the inductor is equal to 0, right there. That's the equation right here, right? And if I carry out this equation, then you get two terms. One is for the on time, the other one is for the off time, right, of the switch. So VL on, VL off. So if you carry on with this equation, then you get this equation right there, right? Now, another thing I would like you to memorize is this equation right there. Based on volt-second balance, VL on times T on plus VL off times T off is equal to 0, right? Too bad we are not on campus, If you're on campus, I see you in the hallway, I'm going to ask you, do the volt-second balance for a transfer function. Very first thing you need to say is this, that VL on times T on plus VL off times T off equals to 0. Please do this, say this at least once before you go to bed, okay? So that way you remember that VL on times T on plus VL off times T off should be equal to 0. Why is that important? Well, check this out. Do you know what T on is? What is T on?
Your duty cycle.
DT.
DT.
Period.
DT. T on is DT. Do you know what T off is?
1 minus
D
dt.
times T.
Very good. See, if you already know what T on and T off, you just need to find two voltages, VL on and VL off. And that could be simply found by looking at the circuit. No need to derive with DIL, DT, and stuff like that we just did earlier. Isn't that cool? Right? So that's why this is a very important starting point for you to remember. Right? Buck, boost, push, pull, forward, flyback starts with this. Okay? You don't need the integral here anymore because you already know, right? How to get there, how to go from here to here, right? So for us, for a buck converter, I'm gonna do this, right? Here's our buck converter. Right? We out there, right? I already know half of the equation. I already know T on. I already know T off. T on is just dt. What is it? Right here, dt. T off is 1 minus d times t, right there. All I need to do now is to be able to find VL on and VL off. What is VL on? VL on is the voltage across the inductor when the switch is on. When the switch is on right there, have a look at the circuit. What is the voltage across that inductor? What is it? Without looking
The
at the
input minus the output.
Very good. Sorry, I forgot to put. When the switch is on, I know that the inductor voltage is equal to V in minus V out. Just put it in the equation right there. See that? Now one more left and you're done. What is VL off? VL off is voltage across the inductor when the switch is off. Oops, sorry, I got too excited there. When the inductor is, when the switch is off, what is the voltage across the inductor? Right here. What is the voltage across the inductor? There's the loop right there.
Negative V out.
Negative V out. That's what you put in right there. See that? Negative V out. Isn't that much simpler than doing this with delta IL? Right? All you need is just two lines. 1, 2, and you're done. Actually, yeah, this is just algebra, maybe 3, and then eventually you get this transfer function. So do this when you get an interview with somebody, some company, they're asking you to derive a transfer function, start with volt-second balance. Impress them with this. All right? Simple, short, simple, easy, and you get the transfer function that way. Any question on this? Again, as I said earlier, this is only valid for ideal condition, steady state, and CCM. That's enough for this class, right? And also independent of load, very important. Any question on this? So from now on, I'm going to use volt-second balance. I'm not going to use delta IL anymore. Heck no, that's too long, right? I'm just going to do volt-second balance to derive transfer function for boost, buck boost, flyback, forward, whatever. Whatever converter you're analyzing in the future, do this, volt-second balance. Easy, right? Okay? Any questions? Only got 8 more minutes. I'm going to explain, hopefully enough time now, to explain how the inductor current shapes like a triangular waveform. Right. Here we go. Start from VL on again. Okay, let me sit down and let me drink my coffee first. Hang on a second here. All right. We've seen this before. VL on is voltage across the inductor when the switch is on. We already know for a buck converter, that's V in minus V out. That's equal to L DIL on dt. So therefore DIL on dt is equal to V in minus V out over L, right? And now we know the output voltage, the magnitude of output voltage with respect to input voltage, right? This is a buck converter. I forgot to mention here that the transfer function is V out is equal to D times V in. The value of D is between 0 and 1, isn't it? Right? So therefore, V out, the best you can get is equal to V in, ideally, right? And then other than duty cycle equals to 1, if duty cycle is less than 1, then you can see that V out is going to be less than V in. That's why this is called a step down converter, right? Because in practice, output voltage is going to be less than input voltage. Hence the name buck converter, step down converter, right? So now, looking at this equation, I know that V out right there must be smaller than V in, right? If V out is smaller than V in, that means V in minus V out must be positive. You agree? Must be positive. Oh my God, let me use the pen. Must be equal to, must be positive, right? The resulting sign of the number of the difference between the two must be positive right there. L, inductance is also positive. You cannot have negative inductance. So positive divided by positive gives you a positive sign, right? Why is it important? Because what I'm looking for is DIL dt right there. What is DIL dt? Anybody? What is that?
The inductor voltage times the inductance.
No, physically, what does it mean? It means the slope of inductor current, right?
Oh, gotcha, gotcha.
Right. So physically, that means is the slope of the inductor current. This will be useful when understanding why the shape of the inductor is a triangular waveform, right? Because by looking at the slope. So the slope of the inductor when it's on turn out to be positive right there. Meaning what? It's increasing. Positive slope means is increasing. But what kind of a behavior when it increases? Is it linear? Is it exponential? Is it following sine wave? What is it? Well, take a look again, right? L is constant, right? So here's constant for sure, right? Once you select L, you cannot change it anymore, so L is constant. What about V in minus V out? Well, we're going to assume that V in is constant too, of course. That way, we simplify the analysis. So given a fixed input voltage, the output is also fixed, right? For a given duty cycle, right? That's why it's called average output voltage. Remember, this is there's a feedback loop that would maintain the output voltage. So we have a fixed input voltage, a fixed output voltage, right? And so therefore, V in fixed minus V out fixed equals a fixed value or constant value. Maybe this is 2, this is 1. So a constant divided by a constant gives you another constant. So now I know that if I operate this converter at a given input voltage, given output voltage, right, then the slope of the inductor current when it's going up must be positive, must be constant or linear, right? This means linear slope, right? Right there, linear slope. Where is it? Right there. Oh, gosh, almost. Right there, linear. That's one thing. Another thing is that since this is going up, that means we are charging the inductor. So this is where we are charging the inductor. That happens when we turn on the switch. So when we are turning on the switch, not only that the source is supplying energy to the load, but it's also charging the inductor. Okay, and that's the shape of the inductor current waveform when it's charging, linear slope. All right, what happens when the switch is off? That's V off, and we know that for a buck converter, when the switch is off, the voltage is minus V out. V out is constant, right? Keep in mind, and is equal to L DIL dt. Now it's DIL of dt, right? So now the slope when the switch is open, that's equal to minus V out over L right there, right? Now tell me, is it a constant slope? Yes or no? Yes or no?
Yes.
Yes, because V out is constant, L is constant. That is a constant. So it is a constant slope. What is the sign of this slope? Well, obviously it's going to be minus, right? So minus constant. How do you draw a minus constant slope? That's just a linear slope sloping down, just like this, right? Okay. And then after that, we turn on the switch again, and of course, it's going to charge again. So you can see now that the reason why we have a triangular waveform on inductor, because it is a linear slope when it's charging, and then another linear slope when it's discharging, right? So now hopefully I convince you that inductor current waveform in a buck converter, as well as boost, buck boost, it's going to be a triangular waveform, right? So here is the look of our inductor current waveform. Pretty looking current right there, okay? We have the average value of this inductor current waveform, right? If you take the average value, that's the offset. And we have the peak value, and we have the minimum value, right? So that's IL min, IL max, and average. So three different quantities there, okay? IL max, IL min, average. We're gonna go back to that. We're gonna go back to those on Thursday, right? Or maybe one more, because this is quick. So now that we know that we have what do you call it, a triangular waveform right there, how do you find the average value, right? So how do you find the average value of this triangular waveform? Well, one way to do it is this. Let me make it smaller, and then I'll be done with this. Right there, you can see that this triangular waveform consists of two trapezoids, right? The first trapezoidal current, right, when it's on, and then the second trapezoid B right there, right? And finding average is none other than finding the average, is none other than finding the areas under the curve and then divided by T, divided by period, right? So that's what I do. I'm going to find the areas of the first trapezoid right there and the area of the second trapezoid, and then divided by a period. Right? And everybody knows how to find the areas of the trapezoid, right? The sum of the parallel sides divided times the width divided by 2, which is right here. Right, that's for the first trapezoid right there, and that's for the second one. Okay, the width here is T on dt, and the width here is 1 minus dt. Right, so you can see clearly from here. Don't forget to divide it by T, and at the end, this is what's important, and then I'm gonna be done after this. That the average the average current through the inductor is equal to IL min plus IL max divided by 2. What is IL min again? That's the minimum point of the current right there. What is IL max? That's the highest point of the current. IL min plus IL max divided by 2, that gives you the average value of that current.